I'll take the opportunity to introduce Jim. So Jim Stone got his undergrad and master's degree at Queen's University in Ontario. He's Canadian, very nice guy, as you would expect. He then moved not too far away from here. He got his PhD at UIUC. Working with some of the people in the astrophysics department there, and then afterwards he was a professor at University of Maryland for quite a while, about over 10 years. After which he did a 1-year stint in Cambridge before moving to Princeton in 2003. So he was at Princeton in the Department of Astrophysical Sciences for quite a while. He was a department chair for a little bit, but then in 2019 he moved kind of across the street, so to speak, to the Institute of Advanced Study. Jim has received many honors. He's a member of the AAAS, National Academy of Sciences, fellow of American Physical Society, American Astronomical Society. In 2018, he was awarded the Dirk Brewer Career Award for his work in computational fluid dynamics in astrophysics, as given by the American Astronomical Society. So Jim is most well known for his work developing some very widely used numerical codes for fluid dynamics in astrophysics. I think the first one was called Zeus. And then the more advanced one that he's going to be telling us about today is Athena. Okay, so you can see there's like a bit of a theme. In addition to developing these numerical tools, Jim has also been using them to tackle a wide range of problems in astrophysics, ranging from star formation to accretion disks. I think the latter of which we'll maybe hear a little bit about today. So I'm very happy to be able to welcome Jim here. So maybe let's you can join me in welcoming.
Thank you for that very kind introduction, and it's great to be back at Northwestern. This is certainly been here before, although usually I visit the astrophysics group Sierra, so it's a great pleasure to be here in the applied math program. Meaning that I've also prepared somewhat of a different talk. I would normally focus on astrophysical applications and more an astrophysics talk. Instead, I thought today I would talk more about the basic methods that we're using and some of the applications we use and some of the challenges to developing these application codes in astrophysics. So that's my title, Fluid Dynamics at Exascale. And I'll just explain the image that forms this background in a minute as I make it through my talk. So here we go. We thought it was working, but it's not. Unable to advance slides. I should check that. There we go.
Okay, now
there we go. Okay, there we go. Okay, so we've had our technical glitch, so all is going to be great now.
We only get one technical glitch per talk. Yeah, so yeah, it'll be fine now.
So to set the stage, I thought I would try to motivate. What is astrophysical fluid dynamics? Say something about the numerical methods, some of the challenges of running an exascale, exciting times in computational science right now, and then an example application and something about the future where things might get interesting in the future. So the motivation, I think, is actually pretty easy because in astrophysics, we have these just remarkable images that sort of lay out for us the challenges. I mean, here's an image of what's known as the Carina Nebula in our own galaxy. It's a region of dense gas and dust. This image is taken by the new JWST, James Webb Space Telescope. So this is actually a false color image taken in the infrared. And what you're seeing, I say dense gas, but it's many orders of magnitude less dense than the air in this room. It's a few particles per cubic centimeter. It's a very large region of gas, which is undergoing gravitational collapse and fragmentation, forming new stars. There's a new generation of stars that have formed previously that's irradiating this and causing it up to ablate and to evaporate. And so understanding the dynamics of this region, requires fluid dynamic methods, basically. Mean free paths of particles here are much, much smaller than collision lengths or than system size. And so this is really a plasma that can be treated as a fluid. And that's just a local image, a small little region Of course, getting an image of our own galaxy from the inside is hard, but we can look at other galaxies to see what they look like. This is a compendium of an HST image in the optical and a JWST image in the infrared and a combination in between. And that little region I showed you before is like one tiny little white blob in this overall galactic scale. It's a very, very small little section of a single galaxy where we're seeing star formation and gravitational collapse, but in reality, the entire galaxy is being sculpted into these spiral arms. There's many regions of star formation. You can see the connection between the infrared emitting regions and the dark dust lanes and the optical. It's a very complicated, interesting mess. And if we really want to understand how stars, how planets, and indeed even how galaxies form, we really have to understand and model the plasma dynamics directly. And that's really the motivating factor. Understanding the visible matter in the universe requires modeling the plasma dynamics. Okay, so how will we do that? What is the mathematical model that's required to treat this? The most fundamental mathematical model would be given by the Vlasov-Maxwell system for the evolution of the phase space distribution function, the phase space density. For a collisionless plasma, the most basic description is this evolution of the distribution function F as a function of position, momentum, and time, as well as the evolution of the electromagnetic fields that interact with the plasma through solving Maxwell's equations. This is a challenging problem in plasma physics to solve this multidimensional system. Fortunately, if the, again, mean free paths are small compared to the system size, you can use a much simpler system of equations, namely the equations of fluid dynamics. In that case, we know the distribution function for the particles will be nearly Maxwellian. And so you can take moments of the Boltzmann equation and derive the hierarchy of 0th, 1st, 2nd moment equations, which are the Navier-Stokes or Euler equations for compressible fluid dynamics, supplemented by Maxwell's equations for the evolution of the magnetic field, Faraday's law, which tells you how the magnetic field is going to evolve. So rather than solving this much more complicated Vlasov-Maxwell system, we only need to solve the equations of compressible MHD, supplemented with an equation of state, which tells us how the pressure relates to the other thermodynamic variables, temperature, density, and so on. Usually an ideal gas law is sufficient for most astrophysical plasmas. They have very simple internal structures. Usually it's just pure hydrogen, so the ideal gas law works very well. But in some circumstances, we may use more complicated tabular equations of state, but they're just built into solving the system of equations. So they should be sort of familiar. This is the same set of fluid equations that you know and love from terrestrial flows. The only difference perhaps is that these are compressible because typical flow velocities are usually much larger than the sound speed in astrophysics, and so you have to worry about compressibility. So we can use all the machinery and all the mathematical tools that we know about for these system of equations to understand how to develop methods for solving them. So perhaps the most important property of these equations is that they're hyperbolic conservation laws. They can be written in terms of time rate of change of some conserved vector u plus divergence of a flux is 0. We know that hyperbolic conservation laws admit wave solutions, and so one of the most basic properties of these fluids is that they admit plane wave solutions. For MHD, there are 3 different wave families that are present: fast and slow magnetosonic waves and Alfvén waves. The wave speeds are anisotropic. The dispersion relation depends on the direction of the wave vector relative to the background magnetic field. That makes things a lot more complicated than normal hydrodynamics, but nonetheless, the same mathematics underlies the MHD equations as the normal fluid equations. So the little movie is just showing you the propagation of a fast magnetosonic wave in which the magnetic and pressure fluctuations are in phase. So you have the largest restoring force, so the wave has got the fastest phase speed, and slow magnetosonic wave where the pressure and magnetic field fluctuations are out of phase. And these movies are actually calculated by one of these numerical methods. These are very weakly, very low amplitude waves, amplitude of 10 to the minus 3, so they're highly linear, and so they just propagate forever for the numerical method. And you can see the method captures these waves, beautifully. You have very, very good properties. Yes.
Okay, so surely I should know this. So I'm a bit embarrassed to ask, but what do you mean that the equations are not strictly hyperbolic?
It means that because the waves sometimes become degenerate, namely there's not always 3 independent wave modes, sometimes there's only 2. That's because sometimes the fast wave becomes degenerate with the Alfvén wave. So that means they're not strictly hyperbolic because the eigenvalues and eigenvectors are not linearly independent in all circumstances. That's what it means by not strictly hyperbolic. That makes it a little more challenging because when you're trying to solve the eigenvalue problem to get what the characteristics are, you have to know whether or not how many you're looking for. And sometimes the matrix singular, it makes it much harder to figure it out. Yes.
This was computed with periodic boundary conditions?
Yes. This is a periodic boundary condition, the wave just wrapping around and around and around. I don't know, I think it's evolved for 10 wave crossing times for this
So
movie.
how does that, if you make it a bigger domain, you have periodicity over a bigger domain, does that change your solution any?
Not in this case because this is an isotropic homogeneous medium. So the wave was just solving the Cauchy problem. The wave will just continue to wrap around as many times as you go for. Capturing linear waves is a really important property of any numerical method because it's such a fundamental property of the underlying equations. But they're not just linear waves that are important. Also, these equations admit discontinuous solutions, things like shocks, contact discontinuities, slip surfaces, current sheets, which are discontinuities in the magnetic field. Those are nonlinear waves, if you like, nonlinear solutions, and their dynamics is also important to capture properly. In fact, that's one of the great challenges of compressible fluid dynamics. Shock dynamics can be very complicated. The classic problem is a shock interacting with a spherical dense blob, shock cloud interaction, and shown as an image of the density in the shock. You can see how the shock is refracted around the cloud and then collides on axis and generates another shock which propagates back through the cloud. The cloud's destroyed by a combination of Kelvin-Helmholtz and Rickmeyer Meshkov instabilities. It becomes a complete mess from the simple interaction of a planar nonlinear shock wave with a cloud. And so numerical methods must both capture these linear wave modes as well as provide accurate and stable shock capturing, which is part of the challenge of methods in this regime. So what kind of methods do we use? Well, there's many possible. An incomplete list would be based on their discretization. You can have methods based on a spatial mesh, like finite difference methods, finite volume methods, so-called central schemes. You can have methods based on a spectral decomposition, either through global decompositions like Fourier transforms or Chebyshev polynomials, or through local polynomials such as discontinuous Galerkin methods, which are becoming quite popular. Or you can have methods based on the Lagrangian discretization, for example, in astrophysics, so-called smooth particle hydrodynamics, where you use particles to discretize the equations rather than the spatial mesh. And there's also complicated mixtures of these methods. For example, in methods based on a spatial mesh, you can allow the mesh to move with the fluid and have a Lagrangian representation, or you can have a mixed Lagrangian Eulerian method, so-called moving mesh methods. And so there's a zoo of methods, and indeed courses can be taught and are taught, I'm sure, on methods for these solving these equations. They all have their strengths and weaknesses. I'm going to strictly focus on so-called finite volume methods in this talk because they've proven to be extremely robust, work very well on modern computers, and are very appropriate for kind of compressible flows we're going to be talking about today. So a quick 5-minute introduction to finite volume methods, just so we're all on the same page about exactly what we're doing on the computer. So the most basic property of these finite volume methods is that the continuous variables U are discretized in the mesh as volume averages. You take the continuous function U and you integrate it over the volume of the cell, and you store the volume average value of the conserved quantities in each cell center. So a spatial or a visual representation of discretization is you store volume average conserved variables at the cell centers. The magnetic fields are area averaged and face centered. They're integrated over surfaces, not volumes. Then they're stored at the appropriate face for each vector component of the vector field. And then you do that because when you make div B, when you make a discretization of div B, that's basically the magnetic monopile density. That's a cell center quantity. And you do this because you can keep methods that keep div B zero exactly by adopting this staggered discretization of magnetic fields on area on the faces of the cell, area average from the face of the cell. And then to update these quantities, volume average quantities, you need area and time average fluxes at each of the faces. So F, G, and H, they're just, again, not only area, but also now time averages of the fluxes computed at the faces of the cells. And similarly, to update the magnetic field, you need line averages of the electric field around the edges of the cube. And so the electric fields, which are used to update the magnetic field, come from line averages of the electric field at the edges and time averages. And again, using this kind of discretization means that the conserved quantities, mass, momentum, and energy are conserved exactly to machine precision, as well as the magnetic flux is preserved to machine precision, which immediately implies that the divergence-free constraint on the magnetic field is satisfied to machine precision with this discretizations. So far, so good. No approximation at all so far. But the issue is, how do you compute these fluxes and electric fields? How do you compute the time averages of these fluxes and magnetic fields? And that's where the heart of the method lies. How do you do this? Well, the basic idea goes back to Godunov, his original first order method. Again, it's very straightforward to understand exactly how this works. Suppose you just restricted yourself to first order, and you imagine that the volume average values are just piecewise constant within each cell, in which case your distribution of conserved quantities would look like this sort of staircase function at some initial time. And then you just treat this as a real analytic fluid dynamics problem. You say that there's an actual discontinuity between each cell. How would that evolve? There's an analytic solution for how discontinuities evolve in fluid dynamics. It's called the Riemann problem. The Riemann problem can be solved analytically and would result in, for example, in this interface, you might drive a rarefaction wave to the left and a shock wave to the right, in opposite directions for these other interfaces and so on. Each interface would behave according to the jumps in all the conserved variables, which you can compute analytically. And then at some later time, all you need to do is integrate these curves over the volume of the cell, and that gives you your new volume averaged value at the new advanced time. You can do this until the waves begin to interact. When the shock wave launch here interacts with the shock wave launch there, then that's not an analytic problem anymore, because now the shock waves are interacting with each other. So you immediately get a CFL condition built into your method. You can only evolve it for a time which is less than the shock crossing time of a cell, a wave crossing time of the cell. But this sounds horribly complicated. I've got to compute all these analytic curves and then do the integral under them. But actually, this is the sort of brilliance of the method. You don't have to do that. All you really need to know is the solution at the interface. Because if you know the solution at the interface, you can compute the flux. And then from conservation, you know that whatever leaves this cell and goes to the other one is the time of change of the conserved quantity in that cell. So all you really need to know is not the whole solution to the Riemann fan, just the solution along the x equals 0 line. And that's easy to calculate very, very quickly and easily from a Riemann solver. And once you know the flux along that line, you can immediately just plug it into the conservation laws and update the equations. Again, this is not an approximation. This is exact. This is only an approximation when you try to approximate F. If you knew F analytically, this is an exact formula. It's only because we're going to use approximate methods to create F that this is a numerical approximation. So that's basically it. That's how these finite volume methods work. You need a Riemann solver. You have to, for MHD, you have to take into account that there's 3 different wave families. You got to be able to calculate the flux that is the solution along the x equals 0 line at each interface. There are various approximate and linearized solvers that people use, a bunch of different names, doesn't matter, just various approximate methods that one can use for these Riemann problems. You don't want to use piecewise constant methods, first order methods. They're useful for testing, but not for applications. Instead, you want to use higher order polynomial reconstruction to calculate the left and right state at each interface that you then feed into a Riemann solver. You want to calculate the structure, the subcell structure, if you like, of the solution and use that to calculate the fluxes at higher spatial order. So there's a whole literature on so-called TVD or total variation diminishing methods for doing reconstruction that's stable and accurate at high order. And then finally, you need a way to integrate the equations in time at high order as well. You can't just use single time stepping because that's just only first order in time. Instead, you want to use so-called strong stability preserving SSP RK integrators are popular. And there's methods up to fourth, fifth order, and so on. Fourth order is very, very popular because it only requires 4 steps to calculate an RK4 time step. Going beyond fourth order requires more steps than order, and that gets to be more and more expensive. So RK4 is sort of the sweet spot. Fourth order methods end up being the sweet spot for these methods. So that's what goes into it all. Then you can test that these methods work well. You can go back to that linear wave solution I just showed you. Instead of just showing you a plot of the wave, you can calculate the error in the wave. You just subtract off the numerical solution from the analytic solution and calculate the L1 error in the solution domain. And you can measure that as you change the resolution, the number of grid points per wavelength in the wave mode. And you see second order convergence for second order methods, and up to fourth order convergence for when you're using fourth order methods for reconstruction and time evolution on these methods. And so you have a very quantitative test of that your method's convergent and accurate. In fact, it converges until round off error starts hitting you, and then it stops converging. So and you can see very quickly you run into round off error. With only 128 grid cells per wavelength, you're already hitting round off error limits when you're using these fourth order methods. And so it becomes accurate, very accurate very quickly. So that's a very quantitative test of the scheme, make sure that you're converging in all the wave modes. You can also compare against Riemann problems. And there's a large zoo of so-called shock 2 problems, which give the evolution of some initial discontinuous state. This is a particularly nasty one developed by Rue and Jones in a paper on testing MHD methods. Nasty because starting from some initial left and right interface, it generates nonlinear discontinuous solutions at each of the 7 wave modes. A fast shock that goes to the left and to the right, a slow shock that goes to the left and the right. So they're labeled here, these discontinuities in the density are the shock waves. There's a contact discontinuity in the middle. And there's rotational discontinuities that don't show up in the density. They only show up in the transverse components of the magnetic field and the velocity. So those are jumps where the density and pressure doesn't change, but the magnetic field changes its direction at the interface. And that's a rotational discontinuity, alphanic discontinuity, and contact there in the middle. And so, again, there's an analytic solution for the Riemann problem, and you can compare this numerical solution directly against that and validate that it's both accurate and stable. And this looks like there's a little overshooting in some of these variables. It's not. That's where there's a rotational continuity right beside a fast shock wave, and so you get a very tiny region of rotation there. So validating against nonlinear solutions is important. And then finally, thanks to some of the work of Daniel, actually, we can also use intercode comparison between, or at least on problems that have resolved solution. That is, you can take known resolved numerical solutions and then compare against those solutions. And a very nice example of this is validation against the Kelvin-Helmholtz instability. That's the classic fluid instability when you have 2 fluids moving with a shear layer in between them, and it produces instability in the interface and roll up into cat's eyes. So this calculation has explicit viscosity, key conduction, and a resolved smooth tan H profile at the interface. So there's no discontinuities initially, and there is dissipation terms that regularize the equations, and so you can get a resolved converged solution to the result. And what's shown in the panel is the KH instability at different times, starting with a single roll up of one wave all the way to sort of transition to turbulence, where you have secondary instabilities that generate very complex flows. And then this is calculated using the spectral code DEDLESS that Daniel uses a lot. This is a converged solution with 4096 squared spectral elements in each in this 2-dimensional domain, converge because you can increase the resolution, you get exactly the same answer. And against this is the finite volume method at 8,000 grid points squared, so twice as many grid points as spectral elements, but nonetheless, at 8,000 squared, it converges pixel to pixel to the spectral result. And then, indeed, you can take the L1 error norms, and you can compare against take the difference between the Deadless solution and the finite volume solution, calculate the L1 error norm, and follow the second order convergence to the solution. Because these finite volume methods are relatively cheap compared to spectral methods, it turns out that even though this is twice the resolution, it's about roughly the same cost. So you can get spectral accuracy in a very complicated problem in these finite volume methods. I think there's more work to be done here. We still have to compare to other methods and it's still more interesting things to do in these kind of comparisons in the future. Okay, so that's the method, and hopefully I've convinced you that they're straightforward to do very rigorous and quantitative testing in various ways, from analytic solution and from known numerical solution. Let me tell you about a few more things that make these methods useful in astrophysics. One of the most important being adaptive mesh refinement. So this allows you to increase the spatial scales in the problem and refine on regions of interest. Suppose there's some elliptical regions where we want to decrease the grid spacing, increase the number of grid cells. Then AMR is a way to achieve that. You can use so-called patch-based, where you lay down patches of finer grid that cover this region. This was the original idea of Berger and Oliger in their AMR papers. Or you can use block-based, where you break up the background mesh into blocks and you only refine blocks into blocks into blocks in a very regular pattern. It doesn't cover the volume as efficiently, but it has many other advantages. Or you could use a cell-by-cell refinement, where every individual cell could be refined on its own. That's the most efficient way to do it, but doesn't necessarily work very well in parallel computers, where things like to happen in parallel, and when you're breaking things up cell by cell, it doesn't really scale that well. So we use block-based because it's just so efficient on modern HPC processors. Patch-based involves these very complicated shapes and overlaps between the patches, which with parallel processing, it's very hard to load balance. With block-based, every block is exactly the same as every other block, and that makes load balancing incredibly easy. And moreover, the different AMR levels only communicate at boundaries through boundary conditions, again, making it really easy to implement on modern HPC systems. So block-based seems to be a real efficient method for AMR, which is what we use. These methods are, yes?
So here you're talking about the spatial discretization. Can you say something about the temporal discretization? Are you able to take different size time steps?
It's also possible to take a smaller time step on the smallest, finest meshes. The implementation I'm described today does not do that. Again, for load balancing issues, if you take smaller time steps, then each block has a different amount of work, and moreover, communicating the boundaries at different time levels gets much more complicated. There's accuracy issues in terms of doing temporal averaging of the fluxes between neighboring levels. And the loss of efficiency of having different time steps sort of makes up for the extra work you have to do by having a uniform time step everywhere. So in our experience, unless you have very, very deep AMR grids that go for 20 or 30 levels of refinement, then doing this single time stepping seems to be okay. Okay, so of course, another very important feature of any HPC method today is parallelization, because almost all HPC systems rely on parallelization to give you the highest performance. And parallelization is achieved in two ways, either through distributed memory parallelization. You assign blocks to different processors independently. They all work on their own blocks separately and then communicate their boundaries once per time step. Or through shared memory parallelization, where on any given processor, the block it holds is also run in parallel on many, many processors on that node. And this kind of mixed or hierarchical parallelism is common on all systems today, on HPC systems. In order to make these block-based methods sort of manageable, it's typical to organize them into some kind of tree, an oct tree in 3D, a binary tree in 2D. That's because you need to know where your neighbors are. And the best way to find your neighbors in a complicated mesh hierarchy is using a tree. So for example, the picture shows how a two-dimensional mesh could be broken up into separate blocks where there's small patches which are being refined through two levels of mesh refinement. And the way the blocks are assigned is through this Z ordering technique, where you would just move in a Z pattern to label the blocks. When you get to this block here, it's being refined into four more. And so when you're on the tree, the first three blocks exist, but then the fourth block is being refined into another level of four blocks. When you use the Z ordering throughout the mesh hierarchy, when using this tree, it makes it really, really easy to know who your neighbors are and to be able to communicate boundaries. But more importantly, it also increases locality and makes sure that the blocks are local to each other on neighboring nodes. So you're not sending messages across a very large network on a very large machine. They're always staying within switches. The blocks are located as close to each other as possible. And what are you sending? You know, your block is working on a collection of cells. You're sending so-called boundary layers or ghost cells. You're sending your neighboring values and you're receiving neighboring values from the neighboring mesh blocks to fill in the ghost cells so that you can calculate your boundary conditions properly. And every time step, you're having to swap these neighboring cells. So parallelization is straightforward with these block-based methods, but it can get somewhat tricky. With AMR, each individual block could have up to 56 neighboring blocks that it touches. So you may need to send up to 56 messages to your neighboring blocks, depending on how the hierarchy is set up. And so you have a little bit of bookkeeping involved, but again, straightforward. So this AMR, yes.
Quick question about that. So
Sure.
what do you do when you have a fine grid next to a coarse mesh as far as sharing boundary data?
I'm skipping a lot, and so that's an excellent question. So whenever you have a fine mesh abutting a coarse mesh, you need to make sure that the fluxes between the two are identical so that you're maintaining conservation. And you always believe the fine solution mesh over the coarse solution mesh, being it's more accurate. And so whenever you have a fine mesh touching a coarse mesh, you would pass not only the data, the cell-centered values, but also pass the fluxes at the edge, and then use the fine fluxes to update the coarse cells on the coarse mesh, right? Because
So does that mean you add the fluxes basically, like if you have two fine ones next to a whole one,
yes,
and you add the two fluxes?
exactly,
Okay.
exactly. So that the total amount of flux of everything is conserved across. So that way, if you don't do that, the coarse flux you compute in this cell does not necessarily equal the sum of the two fine fluxes. So you've got to enforce this synchronize the fluxes to make sure you maintain conservation. So yes, a flux correction step is necessary. If you think about the magnetic fields and the electric fields, they also have to be corrected, and the electric fields are on edges. Again, it gets to be a little bit of a mess, but again, can be, with a little bit of hard work, can be all figured out. Yes. So they have this sort of seeming magic of AMR. Does that mean an AMR solution is exactly the same as a solution on a uniform mesh? That's sort of the underlying assumption. We can just lay down this fine mesh, and it's almost as if we had just a fine mesh everywhere. Here's a typical test problem. Again, a KH instability in which there was an initial shear layer, which is being wrapped up, started forming a cat's eye, but then these secondary instabilities kicked in. So here's the overall shear surface, the density and magnetic field, magnetic field. You can see the AMR mesh overlaid on the, trying to resolve this complicated parasitic secondary instabilities that have broken up this cat's eye. And it's all very complicated, and, you can do code comparisons. But one of my students thought, well, today's processors, we could just do the whole darn thing on a uniform mesh at the resolution of the finest level. What if we did that? That's the solution you get. It's just a single cat's eye. While this KH roll is unstable, there are no perturbations on a uniform mesh to seed the instability, and it doesn't actually grow. The reason why you get all this fine structure is because despite all our care in making sure the fluxes are conserved across the boundaries, there's a truncation error introduced in that process, which is non-uniform. It's different at the fine coarse boundaries than it is elsewhere. And that's enough to seed any kind of physical instability in the problem, and which is exactly what's happened here. this instability, while real, has been seeded by truncation error in the solution. And if you don't have that truncation error, if there are no fine coarse boundaries, you don't get that instability. So it's important to realize the solution is sensitive to exactly the, your errors, truncation errors, and the outcomes can be somewhat different. Yes.
And is this set up with an initial condition that's resolved and or with diffusion?
So this calculation does not have explicit dissipation. So no, it's not regularized in that way. And that's why it's so sensitive to perturbations, because you have instability all the way down to the grid scale, which is not being damped by viscosity. Now, if you had explicit dissipation and you resolved it amongst all the levels, it would be, so that was going to be my next step. If you were using resolved solutions, this wouldn't happen because the truncation error wouldn't matter anymore. It's completely negligible in a resolved solution. But because this is an unresolved solution with a discontinuity unit where the truncation error is large, then these solutions are sensitive to this sort of thing. Yes.
So if the origin of this is truncation error, is it reproducible in the sense that, like, if you did the uniform grid solution with some finite but very small perturbation,
Yes.
would it look similar?
Exactly. Yes, absolutely. You could do that experiment. You could just add random noise to the initial conditions and this rather than just a resolved sine wave. And then it does break up into a messy solution. Yes. So bottom line is, again, the instability is real. This is not a wrong solution. It's just that the initial value problem posed is different in these two cases. One has additional perturbations, which are hard to characterize because they come from the mesh. And this one doesn't have those perturbations. And so the outcome of the solution is different.
So are you saying when I write a code, I should always put uniform disturbance, an initial perturbation, a random perturbation into the code?
For unresolved solutions, I mean, if there's a physical instability that you're trying to model, then yes, I mean, you should be perturbing. I mean,
A lot of times I don't know that there's an instability there. I'm solving the equations.
I mean, I don't think there's a general answer to your question. It depends very much on what you're trying to study. If there's,
It scares me, you're competent.
right? I mean,
You're saying don't trust the code.
no. I'm saying the code's doing exactly what you tell it to do. It's modeling this physical instability. All that happened is I didn't put in by hand the perturbations. The perturbations came out of the numerical method itself. But at the end of the day, do I even care? Probably not. I mean, in any real astrophysical system, the perturbations are everywhere. They're all the time. You saw the pictures I showed. There is no smooth laminar. This solution is very unphysical. I can't imagine any astrophysical system that had no perturbations in it and stays absolutely laminar, even though it's linearly unstable. And so, and the perturbation of perturbations, once go deep nonlinear, it doesn't really matter anymore. They forget what the perturbations were. And so I think this is a more realistic astrophysical solution than this one, to be honest.
I would agree with that to some extent, right? That, of course, in any physical system, you are going to have fluctuation. So the absence of noise is completely unrealistic.
Yes.
Now, the question is, to what extent do you know that the numerical approximations errors
Yes.
are of the same nature as the
Agreed.
physical noise or not?
That's right.
And so one question is, what if you add some other noise to the other system
Yes.
and see to what extent things change or not?
Yeah.
And I'm asking, I think, a similar question to
Something
Mike,
but better.
which is that how do you assure that the introduced noise numerically is of the same nature
Yes.
as what you'd expect to have physically, and you are not introducing kind of different physical behavior?
Right. That's a very good question. And I think a careful study of this would require putting in physical perturbations that you specify the properties of and not allowing the numerics. I mean, the one good thing about, again, finite volume methods is that you know the truncation error satisfies particular constraints. It's always diffusive. So, it's a little more controlled than just random noise. But on the other hand, it's still, unrepresentable. I don't know exactly what it is. So I think a careful study of this would require putting in physical perturbations. I really only showed this to make the point that, AMR is a very powerful but dangerous tool. You have to be very careful with it to make sure the things that you're trying to measure are not being affected by unavoidable non-uniform truncation error that's going to result from having an AMR gush.
Sorry if we are taking too long on out of these conversations, but one of the aspects is because some of it is due to the mesh, you introduce it in a correlated way, right? Because the mesh has some structure, right? And
Yes.
so where these errors occur
Absolutely.
is not completely independent.
That's right. No,
So-
the Fourier spectrum of the perturbations is ugly because it's all confined to the mesh boundaries. And so that's completely, inhomogeneous and has very, very particular spectral characteristics that wouldn't look anything like any kind of natural perturbation. In that sense, it's nothing like what a natural perturbation would look like.
But it might not matter, right?
Maybe
It is one of the
exactly.
questions that we
The only way to
don't know.
really understand that is to know the nature of your problem and know exactly what your problem is depending on.
I got a better conclusion. You need analytical work on your equations.
If you can solve this analytically, that'd be great.
Linearization.
I just want to follow one more question. If you took that uniform grid solution and introduced a perturbation in just the initial condition,
Yes,
would it break the symmetry?
it would. Yes, absolutely.
And would you get a qualitatively similar picture to what you?
Yes, except it would be more volume filling because as we just said, the perturbations in the AMR grid are occurring only in very specific locations. If you put in white noise sort of everywhere, you find this interface breaks up a lot more, over the. So it would not look exactly like this, but qualitatively, the growth rate of the parasitic modes are the same. They grow into the same kind of small scale structures as you see in this image. So the gross and statistical properties of the turbulence resulting from these secondary instabilities look very, very similar, whether the perturbations came from the mesh or from.
Yeah, so that was going to be my last question.
Okay, well, so clearly there's been a lot of thought and interest in here. So let me charge forward with some other important features of these methods. We have AMR. We also have things like putting in particles. We want to be able to follow charged particles in the flow. We want to be able to use Lagrangian tracer particles. And again, those can be added straightforwardly to these mesh-based methods. You can use these Lagrangian tracer particles to follow cage instability, for example, to see, label the fluid and where the particles come from. You can also, as I mentioned, you can follow charged particle motion and look for cosmic ray acceleration, for example, and an MHD turbulence, which is an application that Philip Kempsky is doing. So these particle methods are very important in combination with the fluid methods for MHD. Numerical relativity is also very important for problems involving compact objects. And these AMR methods on block-based AMR is extremely powerful for doing relativity. And so in this code, we've implemented finite difference methods for solving the Einstein field equations to do full numerical relativity solutions. These are high order methods up to 8th order. Since the solution to Einstein's equations are always smooth, then finite differencing works great and you can go to high order with it. And so here's an example of binary black hole evolution using this code on an exascale computer. You can see the binaries doesn't orbit very long before gravitational wave emission causes the black holes to merge, and you can compute the emergent wave spectrum from this calculation, compare it against existing calculations. You see the chirp of the merger and then the ring down phase of the remnant, and you can do conversion studies on this. And so you can do full relativity. And then if you have fluids and a dynamical space-time, you can look at very interesting problems in things like merger of compact objects, binary neutron star mergers, for example. That's because the MHD equations in GR are still fundamentally a set of hyperbolic conservation laws, which can be written in exactly the same mathematical form as the non-relativistic version. So all the machinery, Riemann problems, high order reconstruction, finite volume methods, they all carry over into the full GR-MHD regime as well. And you can have GR-MHD methods that are nearly identical to the Newtonian techniques. Here's an example calculation of the merger of two binary neutron stars done with full relativity. So you're capturing the gravitational wave emission as these neutron stars orbit each other. You can see tidal forces first start stripping some material off the surfaces in this kind of bar-shaped You get these spiral shocks that emerge eventually as the neutron stars get closer and closer. This is their last few orbits due to gravitational wave emission before they start to merge. They merge and form this bar-shaped, rapidly rotating, hypermassive neutron star, and they keep shedding angular momentum as they emit more spiral shock waves until eventually, pretty soon, flip, a black hole forms in the middle. You have an event horizon, and now you form the black hole from this merger process. Again, you can calculate the gravitational wave emission, see how the fluid dynamics is affecting compared to pure vacuum solutions. And so there's a whole set of new problems in understanding compact object mergers that are enabled by these kind of finite volume methods on AMR meshes. And then finally, the thing I've been working on mostly is doing full radiation transport and doing that in the context of GRMHD as well, where again, the rate of transfer equation for the radiation specific intensity I nu again can be written in this kind of finite volume form, time rate of change of the specific intensity plus the divergence of fluxes, where the fluxes are now not only in space, but also in angle, because as photons move through curved space-time, they change their direction of propagation. But again, those terms can be written in divergence form. And so you can use, again, all the machinery of finite volume methods to integrate the rate of transfer equation in a conservative fashion and have conservative methods for doing full radiation transport in GRMHD, which is mostly what we're doing right now. Because of time, I won't really go into much more about that. But so I wanted to say something about Exascale, since that's sort of the new toy on the block, as you were. Nowadays, we have 2 Exascale machines. After many decades of the vendors telling us it was coming, it's finally here. We have Exascale. We have Frontier, a machine at Oak Ridge, which runs at about 1.5 exaflops, and Aurora here in Chicago, actually, Chicagoland at least, which just turned on. It's at Argonne National Lab. It just turned on a few weeks ago for open science. It's another 1.5 exaflop machine. These machines are 1 billion times faster than the machine I used when I was a graduate student. So it's a little embarrassing about how old I am, but that's 1 billion times is, and moreover, 10 to the 18 flops, floating point operations per second. 10 to 18 is a big number, even for an astronomer. So that is a lot of flops, a lot of compute power. The challenge is that these machines use different accelerator technologies, and each accelerator vendor, whether it be NVIDIA or AMD or Intel, they all adopt different programming models. So famously, NVIDIA uses CUDA, but CUDA doesn't run on Intel GPUs and it doesn't run on AMD GPUs. You got to use some other programming model for those machines. So you got to write a different code for every machine. And that's clearly unsustainable. No application scientist has the time to write a different code for every different machine. Aurora has the Intel GPUs, Frontier has AMD GPUs. Even though NVIDIA is by far the biggest market leader, they're also the most expensive. Those are not the largest machines at the moment. So what do we do? Well, fortunately, our computational science colleagues are very adept at solving these problems in software. And there's a new C++ library called Kokkos, an open source library that basically serves as a set of templates and abstractions that allow you to take any C++ code written in Kokkos and translate it into CUDA if you want to run it on an NVIDIA machine, or translate it into SYCL if you want to run it on an Intel machine. You just do that at the build stage. So you write your code in C++, you adopt their abstractions and templates, and then when you run CMake, your code gets turned into whatever it is you want to run it on, including, running on ARM processors like your iPhone. Kokkos will run on your iPhone if you want. So it gives you what's called performance portability. You run a single code and it works anywhere from your laptop to the biggest exascale computer. And so I've become a big fan of this. And the latest version of the MHD code I'm using, called Athena K, is a complete rewrite of this Athena code using Kokkos that enables it to run anywhere. And as I've shown you, it has these Newtonian, special relativistic, and GR, hydro, and MHD solvers. It has dynamical spacetimes for numerical relativity. Like I showed you, it has GR, MHD, and dynamical spacetimes for doing compact object mergers, relativistic radiation transport, like I was mentioning, particles, and so on. It's all publicly available on GitHub and it's all free for anybody to use. And the table just shows you that indeed you can achieve pretty good performance across pretty much any vendor architecture you like without any change of the source code at all. Just by building it for separate architectures, you get very good performance. In fact, this is the number of cells updated per CPU second. This is mega, so many million cell updates, which is a typical performance measure of finite volume codes. How many million cells can you update in one CPU second? And we're reaching 1 billion updates per second per device, not on the whole machine, but just on one GPU. You can get 1 billion updates per second for 3D MHD, which is really remarkable. You can do really big problems on these machines now. Of course, the key is also getting good scaling. So the machines typically have 50 to 100,000 GPUs in them. You got to be able to run across all 50,000 of them to get really good performance. And so having good parallel scaling is very, very important. But fortunately, these finite volume methods scale extremely well because all you have to do is pass your neighboring ghost cells between processors, which is a very small amount of data. And so the communication is a very, very small part of the overall communication. So this is scaling on AMD and, this is on NVIDIA and AMD GPUs. The number to look at is efficiency. The performance on N nodes compared to the performance in one GPU. And you can see that it gets 98% efficiency. And then, in other words, it runs 98% the speed on each GPU all the way out to 4,000 GPUs on this particular case, but we've run out to 32,000 GPUs as we would have gotten it running on one GPU. So again, these finite volume methods are very, very scalable and are very ideally suited for these exascale machines. I don't know if I have time to get to wax poetic here about the software engineering side of this, which I think is somewhat neglected, but I think it's an important issue, and that namely, that the physics that we're trying to achieve, we're trying to model, the hardware, the software, it's all getting a lot more complicated. Students don't always have a good training in numerical analysis to really understand the mathematics behind the methods they're using. And they often don't get good training in basic software engineering. Things like how to use code repositories, which language should you use, scripting versus compiled languages, what are the advantages, disadvantages, how to do continuous integration and regression testing. I think it's getting very difficult nowadays for students to start from scratch and write a cutting edge code that's at the frontier of running on these exascale machines. Back in my day, that was possible. I think it's getting harder and harder. I think nowadays it's becoming a more collaborative era where you have to adopt pieces of other codes or other algorithms to really build cutting edge codes. And it's a different way of thinking. You have to think about the problems differently. And I think that from my observations, it's really important to stick to the simplest, most established methods. There's lots of new things coming online, but then they sound great, but they often don't last very long. And if you sort of put all your eggs in that basket, it may not work out. Stick just to C++. It's not going away anytime soon. And so you're guaranteed the vendors will always have a C++ compiler. Whether they have a compiler for the latest language, I don't know whether they will or not. I always try to stick to the standards and don't use extensions. Avoid external libraries. I use Kokkos here. Okay, there are some libraries like Kokkos and MPI, hard to get around. But after that, try to not, don't use any other libraries because again, you're just building dependencies in your code, which is not good. Most codes are developed by only a few people, a core team. So you sort of want to watch out for what they're doing and supporting them. And I also think that codes become, at least in my experience, very hard to manage when they get to be hundreds of thousands of lines. And small is always better in my view. So try to keep things as simple as possible. If you keep adding features and features, code bloat, and you then have to support all those features, and then you try to move it to a new machine, you got to support all those features. It just gets to be way too much work for an application scientist. Just keep it short and simple as possible. So I don't often get to say these, stand on a soapbox, but I thought I would there. Yes.
Just out of curiosity, while you have the slide up, what courses do you require your students to take?
At Princeton, we recognize this issue about numerical analysis and software engineering, we ended up developing 2 courses in the applied math program. One on numerical analysis for graduate students, which covered a wide variety of techniques for elliptic equations, PDEs, so on, and also another course in software engineering.
Are these 1-year courses or one semester?
Those are 2 courses, they're 1 semester course each. The software engineering course eventually became the most popular graduate level course taught at Princeton. It was taken by typically 100 students a year, mostly in engineering and physical sciences. I think it said there was a real need. Students really, really want to learn this stuff. And there's not that many opportunities to do it. And so I think these courses could be popular. It's finding people and time to teach them. Of course, it's a little bit hard.
What about the possibility of teaching them with people that work in industry? Because I think that people that work for companies like MATLAB or something like that might actually have an interest in those. And in my experience, it also seems that computer science departments don't care very much about some of this stuff.
I hope, are there anybody from the computer science department here?
I hope so, because it's always a fun to kick them.
Yeah. Or is that a question or
Just an observation about this. I think this is actually an existential risk for research at universities because the people that get professorship jobs do not have these skills.
Right.
These skills are paid so much more in the private sector. And so there are new grants from Simon's Foundation and things like that to have basically software engineers that can come to research departments, but they're not treated as full professors or respected like that.
I totally agree with you that finding career paths for software engineers at research universities is challenging but crucial. Again, Princeton has been creating positions for software engineers and embedding them in departments. So there's now 30 such engineers embedded in 30 departments across campus. They're paid for out of the university budget. And they help students and postdocs and faculty develop codes. I think it's a really crucial part of the software and research enterprise. And I think you're right. Universities have to figure this out. I think using industry is a great idea. In fact, we had a hard time finding people to teach these classes, and eventually found somebody who had an industrial background who was interested in working at a research university, and they've been doing a great job in teaching the software engineering course. I do think that things that the code there's various companies that will teach online courses. I think scientific computing is a little more advanced than that. They don't often teach MPI. They don't teach necessarily the things you need to know for HPC. So I think a course on HPC is important. But yeah, I think that, creative ways of figuring out how to do this.
But there are things also that tend to be very specialized when you are optimizing code, right? How much information does your bus carry? Where are you saving things? How do you decrease all of this transfer of energy of data from?
Right.
And that is usually not taught at all.
Well, no, but so there are tools that help you with that. And what the course taught is how to use those tools. There's industrial standard tools, open source tools that help you find those hotspots. And again, teaching students how to use them was the key. Yep.
You didn't mention national labs much just now, but it feels like that's kind of the sweet spot, and national labs can help fill that gap a lot, right? I mean, obviously they developed Kokkos and they developed a lot of these tools.
Right.
And there are, I think, some educational opportunities that the national labs sponsor. I think Argonne teaches a summer course on HPC. I think Lawrence Livermore does something similar for people in the Bay Area. And it feels like, so I agree, there's a big gap here, but I think that there's something that the national labs can fill probably better than industry can, just because it's a little
I would agree with that too. I do think that embedding it in the curriculum during the semester is best for students. Sometimes it gets just a summer school, and somehow that doesn't always happen for all students. They are busy in the summer, they're not. But if it's actually part of the curriculum, one of the courses they should be taking, then I think that just makes it much easier. But you're lucky, you've got Argonne right next door. I can imagine partnerships that you might be able to do with Argonne, and indeed other places might be able to do partnerships with other labs. I think it's a great idea. Okay, well, I'm not going to finish my applications. I think I'm going to have to just through that and head straight to the end, which is, I guess, saying sort of things I've already said. They basically, I think numerical methods are absolutely crucial. And it's exciting times because we have Exascale and we have really robust methods. And so I think and exascale is just the step. I fully expect zetascale 1,000 times faster to be here within a decade or so. There's absolutely no, I think, engineering reason why computers are not going to continue to get faster and faster. So it's a very bright future for computational science, I think, and we should be thinking ahead even beyond exascale. Thanks very much.
We had a really nice discussion. Thanks for putting your thoughts up. So maybe like a quick question, two before we break.
I mean, I don't have a question, but I.
Yeah, actually,
Sorry.
do you want to ask?
I have a really quick question. So when you talk about AMR, you describe mesh refinement, but what about the adaptive aspect?
The adaptive part?
Yes.
Well, so the adaptive part just comes from your decision about what properties of the flow do you want to resolve better. Is there some value of the conserved quantities that would trigger refinement? You always refine regions where the density is above some value.
So does that mean
There's some gradient. That's completely up to you. You can have any refinement criteria you like. Once you've identified a region where your criteria is true, then you just lay down an extra mesh there. It's straightforward to do that. And then the resulting hierarchy of meshes is whatever it is that you lay down. Any block in the mesh can always be refined again into 4 more blocks or 8 in 3D, depending on whatever criteria you choose.
Okay, so the philosophy here is to choose the right refinement criteria based on the problem.
Well, that gets back to this art of AMR, namely, you will get a different hierarchy depending on which criteria you choose. You can run exactly the same problem, choose 2 different mesh refinement strategies, and get 2 different meshes and 2 different solutions. And if that affects the outcome of the things you're trying to measure, that's very bad. You have to then figure out, okay, well, what is the generic refinement criterion you need? This is not discussed very much, and most people don't pay much attention to it, but it's a fact of life that you have to be very careful about what the refinement criteria are and make sure you understand exactly how that affects the solution you get.
Thank you.
I think there's maybe like another class starting soon, so we might have to break. So let's thank you once more.